All right, Unit 2 of Pre-Calculus. In our first lesson, we're going to be talking about power and radical functions. We're really kind of smooshing like three different types of functions into one, kind of. We're not, math is, but there are several different functions that can be defined as a power function or as a monomial function. Are you ready for the slide? Here we go. Here's the slide. Huh. There you go. Pause point. Yeah, so presumably you're back from copying the things down or whatever else, or you're going to wait a minute and go back, whatever, however you work. So the core monomial function, so that's another name for a power function. It's what our textbooks and other textbooks would tell you is that power functions are a type of monomial function, and I would argue I would argue that it's kind of a chicken and an egg kind of a situation. But so I think they're more synonymous than like a square is a rectangle. I think this is more kind of two words for the same thing. So a monomial, to remind you, is just a single term. So just one term, right? One term. Sorry that I matched this color. That's not that doesn't have anything to do with it, right? So it's just one term. So y equals x squared, y equals x cubed, y equals x to the fourth. So the kind of basics before we get into the couple of weird ones where we kind of flip the script and do something a little different are these four scenarios. If n, so we're talking about this n, so n and a are these n's and a's, right? So if the exponent is even, so 2, 4, 6, etc., right? And a is positive, so that front number, then we've got the end behavior opening up, right? It's going up. So if n is even and a is negative, so negative in front of the thing, but we've got an even power, we've got two ends that are opening down, and then we've got S curves on this. So these are kind of like quadratic functions, and these are kind of like cubic functions, but it really applies to any even monomial function. Is going to be something like this. As the powers get higher and bigger, so fourth, sixth, eighth, 122nd, right? What happens is this base just kind of flattens out a little bit more. Let's do an example to kind of show what we're talking about. I think that's what's next. Let's find out. Flip the page. Oh yeah, so it is an example. The next few examples use these same instructions. So I wrote the instructions once. So all these next few examples, we're going to graph and analyze the function, and we want to describe its domain, its range, the intercepts, so x and y intercepts, its end behavior, and where the function is increasing or decreasing. So let's take a look at it. I'm going to grab a graph to sketch some things on, and there he is, the function we're going to be doing. So we're going to make a thought about this. We're going to think about it and get some intuition about it, and then we're going to put it in our graphing calculator to confirm or maybe disprove our intuition and go from there. So this has its A change. Now, if you remember back to last unit, this A change and it being between 0 and 1 means that it is vertically compressed. So this is a vertically compressed thing, and since it's the fourth, it's going to be less rounded. So squared might be like that, and the fourth might be like that. I'm doing a poor job of drawing it, but it's going to be, on this one, there's no translation, so it's going to be vertex is going to be at the origin. Those are all the things that we kind of expect to be happening. So since it's going to be at the origin, we're going to go ahead and draw our axes kind of in the middle of our graph, right? I didn't count to make it perfect. I eyeballed which one of these was the middle. It looks like I did pretty good. We can count to confirm. You can do that. If you're not one of my students, or even if you are, let us know in the comments who you are and where you're watching from and what else we can help you with math. So let's put this in the graphing calculator. I already put this first one in there. So there it is in my setup there. And then if we do the plot, there it is. I've got my window settings to -10 to +10 in both directions. So you can see it's kind of like a quadratic. In fact, let's just for grins and giggles, let's do the same thing but 1/2 x squared just to compare. And I'm going to, for expediency, do 0.5 because it's faster for me to type it in on the calculator that way because I don't have to push the arrows so much. And then squared. So let's compare these two graphs. So that's going to be the red one when I plot it. So you see it's real similar. Now, oh, you know what I didn't do? I was at Alt-Tab. Oh, no, I did do, because I did half. Yeah, so it's compressed. So this one is compressed just as much, but this one is looking a little bit different. So it's a little bit different when it's to the fourth. Now, I'm going to take that one off because it's going to make our lives a little bit easier. In fact, I'm going to go ahead and delete it out of there. Just going to be easier if we look at the table or whatever else. So this is what it looks like. It's real simple. So let's get a couple of reference points to plot it. So we're going to grab those from our table. So I'm going to head to 0. I'm already counting by ones. That's handy. So I'm going to go to 0. I guess I could have just scrolled up because I was close to there already. So, and let's build a little table of values. So let's do the -2 through +2. So X, I'll graph this in a color since I did my axes in just white. So X and Y, and let's do -2, -1, 0, 1, 2, and then let's grab our values. So this should be symmetric, right? So -2 is the same as +2, right? So we really only need the first three. So 8, 1/2, 0, and then it's going to start over and do the same thing over there. So 8, 1/2 or 0.5, whatever you prefer, 0, and then these are the symmetric points. And 8. And so we've got enough to be graphing. So here we go, -1 and +1 and 1/2. So it's here, here, here. That's these middle points. And then 8, I think that's up at the top. 1, 2, 3, 4, 5, 6, 7, 8. So up here. So it starts to climb real quick. And so it looks like this more or less, right? Just get a basic sketch, and that's all we really want when we're drawing these. These don't have to be perfect. If it's at least as decent as the ugly mess that I'm doing here on this drawing tablet and kind of flying off into space with my hands, then you're probably in a good way. Now I'm going to move this over because we've got to list a few things, right? So this is A is positive and N is even. So what is, now we can look at it from the picture to figure out what the domain and range are going to be, but it's always going to follow that pattern, right? Unless it's translated, and then the range might shift or whatever. So the domain for this is all real numbers, -infinity to +infinity, right? It keeps on getting bigger to the left, keeps on getting bigger to the right. The range in this case, the range is 0 to infinity, right? Including 0, because we can put a 0 in there and get a number, right? 0 to infinity, and also that matches the pattern that we looked at before. All right, and you probably have it on the same page, but I need to flip back and see what else are we supposed to be finding. We're finding domain, range, intercepts, in behavior, and where the function is increasing and decreasing, right? Domain, range, intercepts. So the X and Y intercept, right? X and Y intercept. Intercept, there's only one. I'm saying, but there's really only one, right? Is at 0, 0, and it's the same for both, right? We can put it, well, probably better to put it just as 0. They both are at 0. They meet at the point 0, 0, right? Intercepts, what else was there? In behavior. So the limit as x approaches -infinity of f of x is +infinity. So as we're going this way, the graph is approaching +infinity. It matches our pattern as well, right? And the limit as x approaches positive infinity, we already did the -infinity, of f of x equals also +infinity, right? Going up and up and up, right? You might be able to tell, I don't know that I've mentioned this before, but this is kind of why I like to write limit and log and some of these other things in cursive. That way you can tell that all of those letters go in one word, right? And then so it's less confusing to look at. if only barely, right? In behavior and increasing or decreasing, right? Easy money. So it is increasing from 0 to infinity, right? From 0 to infinity, 0 to positive infinity. As we're going this way, it's increasing, and it is decreasing from negative infinity to 0. Remember that we always go low to high when we're listing intervals. So negative infinity to 0, right? Easy money. Let's do the next one. All right. So what is this going to look like? This is odd, and it is A is negative, so it's going to look like this, right? It's going to be something like this shape, right? Something like that. That's what we're expecting, right? So let's punch it in the calculator and see if our expectation is accurate. So this guy, clear it out. Yeah, sure. That's not, I didn't mean to type it in that way, but that's fine. So negative x to the 7th, enter, and then graph the thing. I didn't change my window at all. Look at that. It's beautiful. It looks just like we expected it to look, so we can do our axes kind of the same space. There's nothing weird going on. So let's pop our axes back on there. You're like, why didn't you leave the axes that you had? Well, on some of our graphs that we do here in a minute, that we may want to move it a little bit because, well, when we get there, we'll see. So let's grab a couple points in the middle there. So let's I bet we can just do these 3, and we know with intuition, because we're not going to go way out here to 128. That doesn't seem reasonable at all. It's just stretching really quickly. So -1, 0, 1, that's probably plenty to do this guy. So let's make us a little table. And you're like, well, why would you do one or not the other or whatever else? You look at, in this kind of reasonable range. Now, on a word problem, you may need to shift and make your numbers, hundreds or millions or whatever. But 1, 0, -1. But on something like graphing on this and counting by ones, just whatever points kind of fit in that space. If it's a really compressed thing, then you might have a few more, or a really stretched thing, you might have less, or whatever else. But just enough to just remember that we're just sketching, and that's if you're doing this class to prepare for college or whatever, which is really the main point of pre-cal, other than to maybe have a fourth math class in your high school, and to be doing all those things, right? Something like this. Other than that, to prepare for college, it's gonna change on each math professor is gonna have different expectations for how much of a graph. A lot of them, like they really don't even care that you label it on something like this. Plenty of math professors. I had some that really, they just want you to be able to intuit what it basically looks like, and you would be almost wasting your time as long as you do the intuition to be able to get a little sketch, just so you understand the core concept of what it looks like, right? That's pretty common. All right, so we need the domain and range. So the domain and range in this case, right? Because it's odd, they're both the same. Both of them are all real numbers, are negative infinity to positive infinity, right? So domain and range are both the same. I know, y'all have it on the same page. Intercepts in behavior, it's got the x and y intercepts at 0, and the in behavior and where it's increasing and decreasing. All right, so in behavior, the limit as x approaches negative infinity, so as it's moving to the left of f of x, is positive infinity. This is, since it's an odd one, is they're going to be opposite, right? They're not approaching the same thing. We're approaching positive infinity going to the left, and the limit as we're going to positive infinity is actually going to be negative infinity, right? The limit as x approaches positive infinity of f of x equals negative infinity this time. And it is only ever decreasing, right? It's never increasing. It's odd. Function decreasing. Oops. Decreasing from negative infinity to positive infinity, right? There we go. We get everything we needed. Domain and range, intercepts and behavior, where the function increase. We did it. We answered all the things. Okay, this next one is where it changes. You might be like, okay, I think I get it. Let's move on from this topic. We are actually with this example, I the Matthew. I don't know. Whatever I'm trying, not Matthew, but math space you. I don't know. You got it. It's fine. Who cares? Okay, something else happens. We've got a negative of 2x. So this only sort of matches our that big slide with all the stuff. We've got a negative exponent. What does the negative exponent do? Well, it gives us the reciprocal. So this is a monomial function. This is a power function. It's a monomial raised to a power. Easy money, right? But it's shifting. It's making something different. So what is this going to look like? Well, so this is a reciprocal function. So this is the same as 3 over x squared. So we have seen before 3 over x. We've seen that, right? That would be something that looks like this. That's terribly drawn on, and it's like crooked, but you get it, right? You remember those. You've seen those before. That would be like that. What happens if we square it? So let's see. What do you guess might happen? So tell me what you think it might happen. This is where it would be nice to be in person, but you can let me know in the comments. What do you think is going to happen with this? And let's test and see if you're right. Let's go look at this on a graphing calculator and see what happens if you have an even negative n. So while I'm typing this in there, if it'll let me, okay, fine. What is happening? Syntax error, great. Cancel, whatever you're doing. I don't even know what it was trying to do. As I'm typing this in, let's kind of talk through it. So normally when we have an even n, it has both things open in the same direction. So what we've seen before with that x, that's got an odd n. It's a negative 1. 1 is odd, and it has pieces in opposite. So maybe on this one, there's going to be some things that are going in the same direction. So think about that as we push this in there. So it's going to be 3 and then x to the negative 2. All right. Oops. Yep, syntax error because it didn't type the 2 for some reason. All right. So last chance to tell me what you think it might be before you're cheating. All right, what might it be? Oh, look at that. It did kind of do what it looks like we want to do. I'm going to pause and I'm going to put this on my thing so I can write on it and kind of talk through a bit of this. All right, so I shoved this on there as my sketch. You can draw a quick one on your paper just so you have something to talk about. So normally if this was like, say, 3 over x, right, we would expect there to be something like this here. So what did this do? Well, it took that bit and it put it over here, right? It moved it up. And so now we have something going in the same direction. So it's an even power. So you can, through intuition, what would it look like if we change this to a 4? Let's think. I bet you already know, but double check it on your thing. Let's change that to a 4 and see what happens. Change that to negative 4. And what is it? Well, it's very similar, right? It's a very similar thing, which is what you'd expect. If we change that to a 5th, what's going to happen? Is it going to take that and move it down? Let's double check and see if it does what we think it probably does. So put that as a 5. And then we're going to plot that. It does. It kind of looks like the over x, right? It's a little bit differenty, right? Because it's kind of moved over and it's a little bit different than the just over x to the first. It's a little bit different, right? Remember, if it's over x to the first, or x to the negative first, right? Over x to the first to the negative first. However, you can talk about that either way, right? It's kind of like more even between the things. So it gets a little less even as the oddness goes up. So that's what is happening. Let's do our list of characteristics. So the domain is, now the domain and range are different here, so we can't list them the same. So the domain has got two chunks because we've got some asymptotes here and we've got an asymptote there, right? So it's going to get closer and closer to 0, but never quite get there, and then it's going to get closer and closer to 0 over here and never quite get there, and then go to positive infinity. So our lowest number on the domain, the furthest over it gets, is negative infinity. So the lowest number, we're going low to high, right, is negative infinity. And then it goes to 0, and it's got to be not including that 0 because it's an asymptote, right? It's never going to touch there. It is not continuous there. And then we're going to union that with 0 to positive infinity. So that's the domain. What about the range? So the range is 0 to positive infinity. Now, what about this asymptote? Does that matter with the range? No, it doesn't, because all we're interested in is the up and down, right? So up and down, it goes from 0, not including another asymptote there, and it's going to keep on going up forever and ever and ever, right? So it's 0 to positive infinity, right? That's the range. Now, what are we doing next? I don't know. Well, I can't read that at all. It's great. Intercepts in behavior. Intercepts. So here's an interesting thing. The x and y intercepts, none, doesn't have any. D and E does not exist. There are no intercepts. It never crosses the x-axis. It never crosses the y-axis. It's going to only approach those things, right? So the end behavior, all right, end behavior in this case is going to be similar in both directions. So, but it's going to be different than our other ones, right? So the limit in this case, as x approaches negative infinity. So let's think through what's happening here, right? So as we're getting further and further in this direction, where is it approaching? Because it's not approaching negative infinity or positive infinity. It doesn't keep on going down and down and down, right? It's getting closer and closer to a specific number. It's getting closer and closer to 0. So of f of x equals 0, because as we continue this way, it's getting closer and closer to 0. Now, it doesn't actually get there, right? We talked about that in the last unit. It's approaching it. It never gets there, but it is approaching it. It's going to get closer and closer and closer to it. So the limit going that way, to the right, the limit of f of x as x approaches positive infinity equals 0 again, because again, it's getting closer and closer to 0, never getting there, but it's getting closer and closer to it, right? Now, let's see, the increasing and decreasing, I think, is that the next last thing? Where it's increasing or decreasing? True enough. So it is increasing from negative infinity to 0, right? It's going up here, and it's decreasing on the other side. So it's increasing on the interval negative infinity to 0, and it is decreasing from 0 to positive infinity. All right, I had planned one more example, but I'm just going to kind of talk through it because I think you're getting the pattern and getting the idea. I'm assuming you are. If you want to see example 4, let me know in the comments, and I'll make a quick video just of example 4, and I'll post it as a follow-up to this video. But this guy is an odd negative one, right? So it's going to be it's going to be in the pattern of here and there, right? But is it though? No, it's not. It's not going to be here and there. Why not? It's not going to be here and there. It's actually going to be here and there. And we'll double check the intuition here. I'm not going to worry about writing down all the increasing, decreasing stuff because I think you got that part down. But let's double check to see if it's here and here, because it's going to be flipped over. That x-axis, right, is reflected. So it's this one reflected. Let's see if our intuition is correct. Let's punch it in the calculator. All right, now it's in the calculator. There it is. I don't think I made any mistakes. Let's see if it looks like what we expected. We expected this white bit over here, right? So when we plot that, it looks like what we expected, right? So getting the pattern, again, let me know if you need this example worked out. Let me know in the comments, and I'll make a quick follow-up to this one. But let's look at the next topic, because the next topic is not an example. So radical functions. Now, so why is this topic shoved in the same power functions thing, monomial functions lesson? Well, if you remember, this right here, n is a fractional, the nth root is a fractional exponent. So this is the same as x to the 1 over n, right? And we have a power here of like m, and then it would be to the m over n. So that's why this is shoved into the same lesson, right? That's what's going on here. So you've seen square root function, something that looks a lot like this, where n is even. So the square root, fourth root is going to follow a similar pattern, all those kind of things. But what about odd roots, so cube roots or fifth roots or whatever? So you notice that it keeps the other half. So this makes sense because this is the inverse of a squared function. So if we have a squared function, let me grab kind of a grayish looking thing. If we have a x squared, then it's going to be a parabola, right? Parabola opening up. And if we inverse that, right, flip it over the line y equals x, it's going to flip over to this pink thing, right? But it's not going to include the negative bit, right? It's not going to include that because we can't have the square root of a negative number and end up with a real number solution, right? And so that's what, so this makes sense. What about this one? Does this make sense? Well, it's the same idea. So this would be the inverse of like a cubic function or a fifth function or whatever else, right? So it's going to be the inverse of this guy, right? And so if we take the inverse of that, we take and flip it over that line y equals x, we take it and we twist it over here, then that's exactly what's going to happen. We're going to twist it over here, and this is going to turn into this, and this is going to turn into that. But we keep the negative bits, right? Because you can have a negative inside of an odd root. That works out totally fine. So that's what's happening. That's why this one is kind of missing a chunk, and this one is not missing a chunk. Let's look at some examples of this. So here we have another example, same directions as previous, so we're still trying to find all those same things, the domain range, all the different things. So what is this going to look like? What do we expect this to look like? Well, let's see. We've got some transformations that have happened, right? So, and we've got a cube power. So that's gonna be a, so if it was just that, it would be like this, right? But then we've got the fourth root, so that's an even root, so that we know looks like this. So is it going to be like that, but then with a tail on it, or is it going to be just this? Kind of think it's going to be just this, but let's see, right? And then we've got an A change and a B change. This is vertically expanded, vertical expansion, vertical stretch is the word that's escaping my brain for a second there. Vertical stretch, and then this 5 on the inside would be a a horizontal compression. So it's stretched and smooshed. So he's going to be heading up really quickly, right? Because it's going to be a stretch this way and smoosh this way. So it's going to be going really quickly. So that's kind of what we expect it to be. And that's this. I'm talking through these before I graph, and this is very important. I keep saying this because you need to be able to have an intuition for what this looks like before you graph it. That's really what we're wanting to gain from this lesson, is an intuition for what it's going to look like. So let's graph it and see if our intuition was right. There it is. Now, my intuition was accurate here, right? It was pretty straightforward. This is going to be centered over here. Now we could shift our window over a little bit when we graph it, because we don't need any of this stuff over here. So we could actually draw our axes a little bit different on this one. Give us a little bit more. I didn't mean to keep writing in the gray, but that actually looks fine. I think that's visible enough. Looks like it's visible enough over there on the recording part. So we'll keep it. It's not really what I meant to do, but why not? This way we can graph the thing in white and it'll match this. Not really intentional, but works out fine. So where is the domain and range? Actually, let's get a little chart. I'm getting ahead of myself. Get a little chart with a handful of points. We're going to start at 0, right? Because it starts at 0. Right. So let's go over here and see. Look at that. Nah. It doesn't exist over there. It's great. You notice that the fourth root kind of overrides the cubedness because that's where we get the issue of the does not exist part, right? It's the even root where we have stuff. So I think that I'm going to just include these two whole number points. You won't always have the ease of that, but since I moved my axes, I think I can get to 5 and 10. So I think that's enough to be getting a curved sketch in there. So 0, 0, and 5, 10. I think that's going to be enough to get us a sketch. So 0, 0, and then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. And then we're going to do our best to kind of connect the dots in something of a curvature. Again, you do, if you're using this for college or you're not in my class, then follow whatever the professor wants as far as how much specificity to graph these. Maybe more, maybe less than what I'm doing, but follow that. So the domain and range are the same, right? 0 to infinity, 0 to infinity. So the domain and range are 0, includes 0, right? Because we can put 0, 0 in there. It's right there, right? 0 to infinity. Never including infinity. Both positive infinity, then we're not going down or to the left anywhere, right? And then next, we're looking at whatever we're looking at. Oh, the intercepts. The X and Y intercepts are the same again. X and Y intercept are the same, both at 0. And then the end behavior. This is a little bit different because we only are looking at one side, right? I didn't talk about that on the slide going back. The end behavior on an even root, there's only one direction, right? There's only one part of it because there is no end behavior going to the left, right? Because it just stops. It doesn't go to infinity in that direction. So there's only one set of end behavior. All right, come back to here. So the end behavior, the limit as x approaches positive infinity, because it doesn't approach negative infinity, of f of x is positive infinity. As we go to the right, it's going up and up and up and up, right? Easy money. And it is always increasing from 0 to infinity. We get all the things compared to this. Raising, decreasing. Yep, we did. Look at that. I remembered. Easy money. Except I forgot to put that. All right, let's see what else we got. See what else past me wrote down. Oh, look, it's more complicated. Okay, so what's happening here? We've got an odd root, right? So we're going to have something like this or something like this. Sideways S-curve, probably. And it's going to be this one. Because this A is positive, that change is positive, right? It's going to be vertically compressed, right? Because A is a fourth. And then it is translated down 8, not down 8, to the right 8. It's not up or down any. There's nothing outside of here that goes up or down, right? It goes to the right 8. And then it is horizontally compressed by a lot. So we're expecting something that shifted over and then it's really compressed. So it's going to have this tight little bit. That's kind of what we're expecting. Let's go punch it in and see what happens. See if our intuition is right. So grabbing this over here, there we are. Are we in a good place? We are in a good place. Now, we it's harder to see what's going on here. I think I accidentally changed the window. Let me tweak my window settings real quick. See what we're set at. Let's change it and pause it and come back. So this is what I set it to. So I set it to kind of the same intervals in both, but interval in both direction. But I shifted this one over to the right so that we can get a good look at what's happening here. So when we plot that, it's shifted over. These are counting by ones. Now you notice something interesting here a little bit, or you might notice something interesting here a little bit. Let's pull up the table and see what's happening here. So there's something interesting happening, right? Let's pull up the table and see if we can figure out what's going on. So where does the graph cross the y-axis? Excuse me, the x-axis. So where does the graph cross the x-axis? So where I want to know where this point is right here. Right here, right? So where is that? Well, it's going from negative and it shifts to positive. So it's somewhere between 1 and 2, which is interesting because we said this was going to shift to the right 8 units. Why didn't it shift to the right 8 units? Well, let's see if we can zoom in and figure out a little bit better what's going on. So I decided to kind of get a 2-for-1 learning and throw some stuff out there. So what we have said in the past so far is that the H is the horizontal translation. It is, and it moves opposite of what you'd expect, right? It's -8, which means that we're adding a -8. So, it's moving to it's opposite, or it's minus H in here, and so it's minusing a -8. So it's moving to the right. All that works out really well, but we're trying to find on this graph where it crosses the x-axis. We're trying to find the x-intercept here, right? And so what's going on? Why didn't it move a full 8? Well, I went ahead and did some algebra real quick, right? Remember, to find the x-intercept, all you do is put a 0 in for the f of x, 0 in for the y, and then you solve it for x. So that's what I did here. Divided that 1/4 off, raised to the 5th power to get rid of the 5th root, and then a simple 2-step equation, and we end up with 4/3. So it's actually crossing at 4/3, which is 1 1/3, right? So that's 1 1/3. So it's actually crossing right here. So to find when there's a B change, to find where the new shift is, we're going to set this equal to 0, essentially, is what's going on, right? Now, I said we're going to 2-for in our learning, so that makes sense. That's easy money. But I'm going to go over to my calculator, and I've already gone ahead and punched in 4/3 and gone to 4/3. So 4/3 is right here, right? Let me pull this up on the screen here, and then we can talk about it easier. Give me a second. So calculators are dumb, right? Calculators don't know anything. I don't know if y'all knew that or not. Calculators can only do what they're programmed to do. And so in this case, this calculator is just a titch dumb. And your calculator is probably the same thing. If you follow the same process, put this in there, and then you do that in the table, you're probably going to have the same thing that's happening. Now, if your calculator has a computer algebra system, it might give you a better answer depending on how it's programmed. Now, a lot of calculators, they kind of are not really important to the company. You know, TI, that makes TI calculators, their actual business is microprocessors, microchips, and whatever, all that stuff, semiconductors. And Casio, their main thing is watches and cameras and all kinds of stuff like that. And HP, they make computers, right? So they have this. So all these companies, like, their calculator division is an afterthought, and so oftentimes they're kind of junky. Like, there's something that you could have built in the 80s. In fact, a lot of them were built in the 80s or earlier, right? And so if we look at this, it is not 0 right here, and you're like, wait a minute, did I do something wrong? It's negative 1.8 times 10 to the negative 3. So really pretty small number, right? And so there's two things that are happening here. There's a rounding error inside the calculator. It's not me, it's not you, it's not it's the calculator. The calculator gave us an error, right? And so we've got to be able to trust the algebra and what's going on. So let's stick a few points that are around there. Are there any, let me go back to my calculator. Are there any whole number points in here? Let me go back to counting by whole numbers. What is happening? And pause and come back. So I don't know what's going on, but we're counting by ones, and I found me a whole number-ish, a whole number and a simple fraction, -4, -half. So I'm going to go ahead and toss that one on there. And it's going to be symmetric about the origin. Now the origin is now over here, so I'm going to kind of eyeball the rest. So -1, 2, 3, 4, -1/2. And so something very similar over there. So it's going to look something like this. If I can kind of connect my dots, and then it's got a little bloopy doop right there, and then it continues on that way, right? So something like that is good enough for our sketch. Easy peasy. So that's what's going on. That's what we got. Let's write our domains and ranges and all the things, and then we'll keep on moving. So the domain and the range are the same here. They're from -infinity to +infinity. The x and y intercepts, x-intercept, we just calculated through the math. You can go back and show where we got that from. The x-intercept in this problem is at 1 1/3 or 4/3. The y-intercept is at 0, right? Still crosses at 0. Easy money. Okay. And then the limit as x approaches -infinity of f of x is -infinity. It's getting smaller and smaller very slowly, but it's going to get there eventually. You can't actually get to infinity, but that's where it's headed. It's getting lower and lower slowly as x approaches +infinity. Can y'all hear my dog snoring? F of x, oh my gosh, I got notifications. I may need to pause and turn that off. It's going to +infinity. As we go to the right, it's getting bigger and bigger and bigger. It is increasing always. So from -infinity to +infinity. All right, we got one more thing real quickly. These won't take very long. We're just going to remind you how to solve, do what I did just a minute ago on that kind of pseudo example, solving a radical equation with a root in it, right? So what we want to do first, if possible, is, we want to isolate the root. So that's what we're going to do here. So we're going to add 2 to both sides. This is probably mostly review, so I'm going to kind of go a little bit quickly on these, but it's probably mostly review. If not, you can go watch my Algebra 2 videos on the same topic, solving radical equations, or somebody else's videos, or whatever else, or read the book, or any number of other ways. So now that we've isolated, and this is where it gets a little bit hairy scary, right? Because we're going to end up squaring both sides, and we're squaring this binomial, and so we're going to have to factor a quadratic formula or something. You'll make it. It's going to be okay. So the opposite of square rooting is squaring, so we're going to square both sides. And so on this side, we've got a binomial. Now I'm going to use the shortcut here. If you want to split this into 2x plus 2 times 2x plus 2, and then FOIL it on out and do all of that, that's great and not a problem at all. But I'm going to use the shortcut for squaring a binomial. So the first part is this one squared, so 4x squared, and then the middle term is 2 times this times this. So 2 times 2 times 2 is 8. And then 2x times 2 is x, so it's got an x in it, right? And the last term is this one squared, so plus 4, because 2 squared is 4. Now the square root is gone. We've got 100 minus 12x. Now we got to move all of this over with their friends, so we can either quadratic formula or we can factor. If we're real lucky, it'll factor. So we're going to subtract 100 from both sides, subtract 100 from both sides, add 12x to both sides, Add 12x to both sides. Now what do we have? So we've got 4x squared. I'm going to kind of move this over a little. 4x squared. 8 plus 12 is 20, so plus 20x. And then 100 minus 4 is minus 96, right? Now, we've got kind of a mess here, right? So can we reduce this any before we start trying to factor? Well, they're all at least even, so they're all divisible by 2. Are they also divisible by 4? Well, of course, yes, they are, right? Because they're all 4, 20, and 96 are all divisible by 4. So we can divide everything by 4. Now, we're dividing this by 4 as well, but 0 divided by 4 is still 0. So he's not going to change. So 4x squared divided by 4 is x squared. 20x divided by 4 is 5x. And I already sanity checked. 96 divided by 4 is 24, and it is 24. So minus, watch your signs. That's an easy place to make a mistake. Minus 24 equals 0. So we're going to factor this. This is nice and easy because as a is now 1. That's really super duper handy, right? So we're going to put an x and an x. What are our options for 24? 24 and 1, 12 and 2, 6 and 4, 8 and 3. Ooh, I can see some addition there. 8 and 3. We can smiley face, guess, and check. 8 times 1 is 8. 1 times 3 is 3. We're trying to add or subtract to get that 5. Does it work, or can it work? Minus and plus will give us positive. If 5, follow our mouth and put negative. Follow our nose and put positive. Now we got to double check that sign at the end. Positive 8 times negative 3 is 24. So x equals negative 8 and positive 3. Now, it's important with a square root that we check these to make sure they work, because sometimes they might not. So we're going to do a check to make sure. Again, this is pretty review, so I'm going to kind of speed run it, right? So 2 times negative 8 is negative 16 equals the square root of 100 minus 12. Negative 12 times negative 8 is positive 96. So 100 minus 96 minus 2. So this, 100 minus 96 is 4. Square root of 4 is 2. So negative 16 equals 2. Then minus 2 equals, minus 2 equals 0. So negative 16 equals 0. So either I made a mistake or this one doesn't work. Let's double check our work to make sure we didn't blow it. So I did make a mistake. You probably already noticed. I made the mistake that I caution y'all against, and I like to leave these things in here to remind you that everybody, first of all, everybody makes a mistake. It makes mistakes. And second of all, really watch those signs, because that's exactly what I did when I was plugging negative 8 in here. Negative 12 times negative 8 is positive 96. So this would have been the square root of 196, which is 14. 14 minus 2. Now, it still doesn't work. So what's going on? Did we make another mistake? Or is how incompetent am I? Well, this time I wasn't incompetent. Oh, I don't know why I had that up there. This time I wasn't incompetent. This one just doesn't work. This one, there's not any more mistakes, right? This one does not work because of signs and all the things and how square roots work and all of that junk. So what about 3? Does it work? So let's put 3 into there. 2 times 3 is 6 equals, let's see if we can do our signs right this time. By we, I guess I mean me. Who knows? 100, and then negative 12 times 36. Negative 12 times 3. Negative 12 times 3 is 36. So 100 minus 36. And then the minus 2 out there. So 100 minus 36 is 64. Square root of 64 is 16. No, it's not. Square root of 64 is not 16. 16 times 16 is 256. The square root of 64 is, in fact, 8. 8 minus 2 is, in fact, 6. This one works. So the only answer is a 6. Or excuse me. Is a 3. These videos, I start saying dumb stuff by the end of them. They're long. They're long. That's how we roll in pre-cal. Here we go. Next one, we got a couple more examples, and then we're going to be out of here, right? So now we've got this with a cube root. This is actually a 2/3 power, so you could actually do it that way if you wanted and get rid of both at the same time, but then it might get a little bit weird, but it is a number. Let's do what I'm talking about and show you instead of just saying words. So again, we got to isolate that radical, right? So subtract 14 minus 14. And 50 minus 14 is 36, so equals 36. And then I'm going to convert this to a rational exponent. So x minus 5 to the 2/3. Remember, the denominator is the root, the numerator is the power, right? All right, so what this is going to allow us to do is get rid of this whole thing in one step. Now, there's going to be something we're going to have to make sure we remember whenever you either skip steps or you combine steps, kind of. This is arguably not really combining steps. This is just doing it in a different format. But whenever you reduce your work, make sure you slow down mentally enough that you don't make a small mistake, because here we're going to raise both sides to the 3/2, right? Because 3/2 times 2/3 would be 1, so that cancels it. So what this is, now let me remind you what's going on here. This would be we're square rooting it and squaring it, right? So that's what we're doing here. But it's important to remember, when we do an even root of both sides, then you end up with plus or minus. So it's going to be plus or minus whatever this is. Now, I already sanity checked this in the calculator. When you do this, it's 216. I double checked before I said you could do this. It's just to make sure I'm not leading us astray. So plus or minus 216. 36 to the 3/2 is 216. And it's plus or minus because it's an even root, right? So now we've got x minus 5. So we add 5 to both sides. I'm going to go ahead and write this one out all the way just to make sure we remember to deal with the plus or minus. So we've got x equals 216 plus 5, which would be 221, and to negative 216 plus 5, which would be negative 211. Now we got to do that check to make sure that they work. So here's our check over here. Plug in a 221. So 221 minus 5, we got the cube root of 221 minus 5, which is 216 squared plus 14. So this is the opposite of doing what we did before, right? So the cube root, I'll go ahead and write it down in radical form in my calculator, of 216 squared. This should work, right? Because this is just the opposite of what we did. So this should give us 36, right? That is to be expected. So 36 plus 14 equals 50. 36 plus 14 does equal 50. This one does work. Great. Now let's plug a negative 211 in here. Is that going to work? So the cube root of negative 211 minus 5. So negative 211 minus 5 is negative 216. Negative 216 squared. Now this is also going to work, and we're going to not into it, but we're going to knowledge our way into the answer. So you might be like, this is not going to work. We got a negative inside of a radical, all these things. Well, so for two reasons, it's going to work. For two reasons, and it's going to give us actually the same positive 36, because negative 216 squared is positive whatever giant number that is, right? And so the cube root of a positive is still a positive. But even now, it would give us a wrong answer in the end because this would end up being negative. But because we're squaring it first, it comes out positive. So it comes out positive 36 plus 14 equals 50, which also still works. So since we're squaring that negative, both answers actually work. And that's often going to be true when we start out with odd roots. Not necessarily always, but it's much more often going to work out, right? Let's do the last example. This one is the most ugliest, and then we're going to be through. All right, this is wild and crazy because we got 2 square roots in there. At least they're square roots and not something larger. All right, so what are we going to do? Well, we've got to isolate one of them, and then we got to square both sides. So one of them's already isolated, so we can jump into squaring both sides. So square this side. That's easy money. That's a 2. It's kind of getting cut off there, but that is a 2. And then we square this side. Now this side, we're going to want to kind of do in a scratch paper space because we got a lot of junk here. And this one, I'm not going to do the shortcut this time because we got this square root. Now this side, I'm going to go ahead and put it down so I don't forget what I'm doing, right? So x minus 2 equals. Now this one, where I'm going to actually do it all, I'm going to do the long cut and FOIL this all the way out. So we've got 5 minus the square root of 15 minus x times itself, right? That's what squaring does. 5 minus the square root of 15 minus x. And then we've got to FOIL it. First, outside, inside, last. Big old distributive property, right? 5 times 5 is 25. 5 times the square root of this is 5 times the square root, well, 5 times 5 times negative square root of that is negative 5 times the square root of all that. So negative 5 times the square root of 15 minus x. And the negative square root of that times 5 is the same thing, right? Negative 5 times the square root of all this mess. Now you can see what's probably going to happen. We're going to end up combining like terms. So we probably could have done the shortcut, but I want to make sure on this one, because it's ugly, that you understand what's happening. I know this video is getting really long, but here we are. Now this times itself, negative this times negative this is positive, right? And square root squared, because this times itself is square root, cancels. So when we do this times that, it's just the inside because the square root cancels out. So plus 15 minus x. Now we've got all kinds of things happening here. We got some like terms. So this one is alike with this one, and then this is alike with this. This little minus x term isn't alike with anything, so he's just going to hang out till the end. So 25 plus 15 is 40. And then negative 5 minus 5 is negative 10, blah, 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 right? Negative 10 times the square root of 15 minus x. And then the minus x doesn't have any friends. So sad. Bring them there. Now I'm going to shove all this over here, right? So 40 minus, almost made a mistake. Almost wrote a 4. Minus 10 times the square root of 15 minus x, and then this minus x out here. If you're not careful, or if your handwriting goes nuts, though, you'd be tempted to put these together, but this one is inside the radical, so you can't put these two together, right? So what is our next goal going to be? Well, it's going to be kind of like on the last one, where our goal is to get the radical by itself. So let's start moving everything off. So let's get rid of the 40 and get rid of the minus x. So we can subtract 40 from both sides, minus 40, and then we can add x to both sides. So this one cancels, 40. This one cancels. X plus x is 2x. I almost said x squared. Negative 2 minus 40 is negative 42 equals, all that's left is the negative 10 times the square root of 15 minus x. So we still have one thing attached to the radical. That's this negative 10. And he's attached through multiplication. So we're going to divide him off -10. We've got to divide everything by -10. But I'm actually going to leave it like this. I think that's going to be a little bit easier if I'll write the right number. It's going to be easier when we do the squaring thing and all that stuff here in a minute. If we just leave it kind of as this weird compound fraction, I think that's going to make our life a little bit easier. 2x minus 42 over -10 equals the square root of 15 minus x. All right, so now we've isolated the radical. We can square both sides. It's getting a little ugly, but you can handle it. It's going to be all right. Just one piece at a time, kids. One piece at a time. So we're going to square this. Now, this, we might also scratch paper over here, right? Because this, we got a binomial on the top, so this has got to be squared. Actually, I say that. Let me back up. We'll just use the shortcut on this one because that's easy peasy. So I'm not going to worry about pulling it over here, right? Let me use a shortcut. And then in the bottom, it's just -100 squared. I keep saying the answer instead of the thing. -10 squared, which is +100. So on the top, using the shortcut, in the right color, yes. Using the shortcut, the first one is this squared, so 2x squared is 4x squared. And then the middle term is 2 times this, so -2 times 2 times 42. I'm making mistakes, so I'm going to punch that in the calculator. 2 times 2 is 4 times 42. Oops. Lesson in that for you is if you're tired and you're doing math and you've been doing math for a while, don't sanity check, and that'll make less careless mistakes. So negative 168x, and then plus 42 squared, because it's this squared. It's always going to be positive, because even if it's negative, negative times negative is positive. So plus 42 squared, which is whatever 42 squared is, something large. Enter. 1,764. 764 over 100 equals 15 minus x. So we want all this over there, and we don't really want this 100 here. So we're going to first multiply everything times 100, right? Just to clear our fractions. So we're going to multiply this times 100 and this times 100. So when we do this times 100, then it cancels here. But this times 100, we got to distribute, right? So we've got 4x squared minus 168x plus 1,764 equals 1,500 minus 100x. Now, hoping this is a factor, if not, quadratic formula. So either way, we want to move all this junk over there. So minus 1,500 plus 100x plus 100x. It's like we're getting a lot smaller numbers. I'm going to move up over here. So 4x squared minus 68x plus 264 equals 0. Now, are all these divisible by 4? They're definitely divisible by 2. They are, in fact, divisible by 4. You can take my word for it, or you can check it on your own calculator. But we end up with, we divide, oops, got to keep writing that. Divide everything by 4. We end up with x squared minus 17, right? Yeah, 17x plus 66 equals 0. And then we can factor the thing. X, and you can walk through this, but as you're getting intuition, especially with a being 1, you can probably see that it's going to be 11 times 6, which gives us 66, And then if they're both negative, we get negative 17 in the middle. Negative times a negative is positive. That works. So this factors into x equals 11 and 6. So to check those, you punch them back in there. But I will save you some time and trouble, and to know that I'm going to put check here and maybe put exclamation point or something so that you remember that that's the thing that you're supposed to do. When you check them, they actually both work. So that is that for that. And we are done. It's the longest one we've had. I'm sorry these are long. Again, it's just how this rolls. We will see you in class if you're one of my students. Otherwise, have a great day. Let us know how you're doing. Goodbye. So long. Farewell.